Okay, so now we're going to look at the Doppler effect for light. But first, just a reminder of the Doppler effect, or if you've never seen it before. Basically, the way I would think about it is the frequency is going to, and the wavelength is going to look different here compared to here compared to here. You're not going to hear the same thing. You're going to hear it differently. And if you listen to a car drive by, you can kind of observe that. Now this is the classical Doppler effect for sound waves. But light is also a wave, right? So we'll see how there's relations there. First off, the equation for the classical Doppler effect is, we'll call it frequency prime is equal to our frequency times V plus or minus V naught all over V minus or plus V sub s. So what does this mean? Well, let's talk about that first. So F prime, that's the frequency heard by an observer O. Heard by, fix my pen, forgot my B, V, observer O. F is the frequency by the source. So F prime might be this kid. This could be your F or source. V equals the speed of the wave through that medium. So speed of wave through that medium. Maybe it's air, maybe it's water, whatever it might be, usually air. V sub s is the speed of the source oops, it's not lined up, relative to the medium. Okay, so we know what this is, 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 and this, and then lastly V sub naught. That's the speed of the observer relative to the medium. Cool. So we broke down what our classical Doppler equation is. If you guys want to know more about the Doppler effect for sound waves, that can kind of be its own video. But that's kind of more classical physics. Since we're dealing with modern physics, we're going to look at this, consider it, but more importantly, is we're going to look at the Doppler effect for light. Okay? So here's how I think we should do this. Let's consider the first picture. Now let's just say we have this source, and we have something like this, where this is the first wave, this is the second light wave, and their wavelength, we'll say, is lambda naught. And then just over here, we'll put in an observer O. So here, the light source and observer are stationary. Now let's look at another picture. So that was picture 1. Let's also consider picture 2 here, where we have same source moving at a velocity v. Okay, so here's what happens. It emits this first wave. Let me draw it actually a little closer. It emits this first wave, and then right when it emits the second one, it gets this little push. And let me try spacing this out a little bit more. So you have, let's see if I can draw it a little nicer. You have the first wave, then you have the second. And we'll call their distance apart the wavelength, lambda. Now the time from here to here is going to be v times delta t. That's just the speed that the source is traveling times that time. Now the distance for the actual wavelength will be the speed of the wave times whatever the time is, and the speed of the wave is just c. And again, we have a source O. Now we'll say the source moves at a speed v, and the observer is stationary. Well, if we look at B, we could say, to find the wavelength lambda, we could say that's our c times delta t minus our v times delta t. So if we take this whole bit and we subtract just this bit, we're left with our wavelength. Hopefully that makes sense. We could factor out a delta t, and you get lambda equals delta t times c minus v. Now also let's remember our equation with time. Delta t equals delta t naught all over the square root of 1 minus u squared over c squared. So this guy, this bit right here, all this stuff can be substituted in right here. But before well, let's go ahead and do that actually. So we get lambda equals delta t naught times c minus v all over the square root of 1 minus u squared over c squared. Okay? But let's think about what delta t naught is in terms of a wave. Well, the time is just 1 over the frequency. And let's remember frequency. Frequency is the speed over the wavelength. Okay? So in this case, be that. So we could say that this is equal to lambda naught over c. But then I can take this, which is equal to this, and plug it into this. Hopefully that makes sense. I think it does. So then we can say lambda equals, so here's how I'm going to do it, c minus v over c times lambda naught all over this stuff. Okay, so hopefully that makes sense so far. We're solving for the wavelength, and then we can relate the wavelength to the frequency to get our equation. Now, quick little algebra. Let's make a note that the square root of c squared is just c. So then I can say lambda is equal to c minus v times lambda naught all over the square root of c squared times 1 minus u squared over c squared. So I just plug this into the radical. I can go ahead and distribute that. So that'll be c minus v times lambda naught all over the square root of c squared minus u squared, which I can rewrite with exponentials as just being to the 1/2. Okay, so now that we have that, we can say lambda is equal to c minus v times lambda naught all over, if we simplify this, what we'll get is c minus u to the 1/2 times c plus u to the 1/2, since which inside is the difference of squares. Now that's nicely just lambda naught times what? The square root of c minus v all over c plus u. Or I'm sorry, u. Okay. Cool. Alrighty, so let's see. Now that we have that, so just to be consistent with the book, instead of v, they use u. And also, if I were to use v, then this would have to be v, but we're going to call it u. So just for the record, these are u's, blah, 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 and then we get here. So let's work through this. Lambda equals lambda naught, the square root of c minus u, not v, over c plus u, which we can just say is the frequency is equal to f naught, the square root of, sorry, this is plus, this is minus, and now we flip it. So we have c minus u over c plus u. Okay. This is when the source and O move towards each other. And then f equals f naught square root of c over c plus u. Oops, plus minus. So this is when they're moving towards each other, and then this is when they're moving away. So it's just flipped. Okay. Now, I'm going to rewrite it a little bit so we see it closer to how the book has it. So the book does a little more algebra, what I'll work through here. The square root of c1 minus u over, u over c, 1 plus u over c. The c's drop, so you get f equals f naught, the square root of 1 minus u over c, 1 plus u over c, or by the same logic we did before, just with this new notation, f equals f naught, 1 plus u over c over 1 minus u over c, depending if you're moving towards or away from the source shards. So yeah, that's pretty much all there is to it. These are the main equations you'll be using. I think the book does it a little bit differently, but I like how this derives the problems a little better. I did want to keep the same variables at least, so that's good, and then we'll do a example problem next.